Good afternoon to everyone in Singapore. I'm really sorry I can't make it to your great conference. Once again, the SAS has exceeded itself in putting together a great conference and some really great presentations. I'd like to start by saying that I'm privileged and honored to be able to speak today. So thanks for the invitation. Just checking, Joey, can you hear me very well? Is everything loud and clear?
Yes, please go ahead.
Okay. Super, thank you very much. So, thanks very much, Sashal, for a great presentation just before. I can say for myself that I am now even more motivated to understand the impact of climate risk on individuals, and if each of us in their own area of expertise contributes to the difficult questions that you've raised, I think we can really make an impact. So thank you for your presentation and also for mentioning mortality and morbidity as a risk that we need to get to grips with. That's my topic today. And I'd like to just start by giving you a quick overview of why I'm interested and why I think you might be interested in modeling mortality better. The body of my talk will be about a case study that we recently completed for a Canadian life insurer, where we analyzed their universal life portfolio, both with respect to lapse and with respect to mortality. And the mortality aspect is what I want to introduce today. In particular, using methods that have actually been in use in the UK market for the last 15 years, and which the Institute and faculty have been using to graduate their tables even since the 1980s, we're actually able to learn more and more about the behavior of portfolios. And we've, in this instance, been able to quantify the impact of anti-selective lapse. I think this is something that for a market like Singapore, where universal life and savings products are the mainstay of the life insurance industry, that's something that's quite important to understand and hopefully relevant to your own work. I can't leave you without taking a peek at Singapore mortality and compare it to a couple of places that are particularly interesting to me, including Australia, Canada, because that's where a lot of my recent projects have been. And you can't talk about mortality or longevity without also mentioning Japan, who at the moment seem to be the forerunners in longevity. So, just trying to move the slides. Here we go. So, I'm obviously motivated to model mortality because that's what I do. But there are other reasons to actually be interested in this. Obviously, the last couple of years have seen an increase in public interest in anything to do with mortality, excess mortality due to the pandemic, but also mortality trends and the impact on longevity with respect to pensions or annuities. As there is, as we just heard, however, a really important elephant in the room, which is the impact of climate change on mortality and morbidity. And using modern techniques, I believe that we can actually identify that impact, quantify that impact, and make it properly measurable. Normally you get the references at the end of the presentation, but I would really like to point out that this is work that's been ongoing, and there's a lot of publications about that. And if you're interested in trying some of the stuff that I'll show you out yourself, a Practitioner's Guide to Statistical Mortality Graduation that my friend Stefan from Ottawa actually wrote, which is published on the SOA's website. That's a really great starting point. Okay, but for now, before we jump into the case study, I just wanted to point out that this is particularly relevant to me and Joey, with whom I've been working for the last couple of years on the mortality working group, because we're in the process of graduating or collecting data to then graduate the new life tables for Singapore. We're being assisted by this, and the brunt of the work is actually being done by Dr. Jade Neer and Professor Shimichi, at Nanyang Technological University. And this is a really great collaboration, which I think is something that's quite unique. This collaboration across industry, professional body, and academia. So I just wanted to say that this is also a great opportunity, and something where Singapore is a forerunner. But if we virtually depart Singapore for a second, think about a Canadian universal life portfolio. Let me just briefly introduce you to what the data was that we used to analyze the mortality, and then show you what we actually found. So you'll see that I try to use as few words as possible, even fewer formulae, and I'm a big fan of cartoons. So the four main risk classes that we're going to analyze are shown in the left for pie charts: gender, smoker category, the cost of insurance type, whether premiums are paid on a risk premium basis. The jargon for that is annually renewable term, ART, or whether the premiums are level for the duration of the policy. And then our client actually had 3 generations of products, which we loosely called legacy products that were in runoff, current products, which was the mainstay of their business, and new products that they'd recently developed. And we wanted to understand what the differences in experience were for those different products. These pie charts refer to the distribution by lives, but obviously when we're modeling mortality for financial purposes, as we actuaries do, it's really important to get a handle on the amounts. So this is a graphic display of the distribution of lives by amount band. Now what we did is as you always do, you sort all the lives that you have by policy face amount, as they say in North America, or sum assured, and then try to divide them up into buckets that are reasonably the same size. On the left-hand side, you see the distribution of these lives into the different buckets. You'll also see that I didn't quite succeed in getting the same sizes. That 100 to 150,000 bucket here, this one, which has 32% of all lives. That's the biggest simply because 100,000 is a really popular number for the policy face amount. Right. So it's a bit lumpy, but the key piece of information that I want to highlight on this chart is that if you weight the policies by their face amount, that group with the largest face amount, which only makes up 12% of the entire portfolio, actually owns 40% of the policy face amount. So there's a great weight on this particular group. That's something that's really important to keep in mind, so that we make sure that when we're modeling mortality, we're actually accounting for this concentration risk. Just a quick overview of the different risk factors that I've just talked about. We've got gender, pretty much evenly split. We have a total of 226,000 lives in our study, which we studied over 3.5 million life years. And they split very unevenly into non-smokers and smokers. The smoking portion of males is greater than females, you can see up here. And then these again split into the level cost of insurance versus the risk premium cost of insurance products, and then into the different amount bands, with the biggest one being the amount band that includes $100,000. Okay, so but that's just the data itself, the raw data. Let's take a look at the risk aspect of the data. Now, I mentioned that we have 3.5 million life years of exposure. So what you do is you look at how much each life contributes to each age bucket or policy duration or calendar year, and then group these exposures into age bands, policy duration bands, or calendar year bands. On this chart, we're actually seeing age on the x-axis. On the left-hand side, we've got the time lived or the time exposed to risk, and it's really important to look at the raw data like this to make sure that you've actually got a consistent set of data that you're modeling. If you have unusual patterns that you don't understand, then chances are it's got something to do with either the data quality or the way that you've prepared the data. And as the person doing the work, I'm always worried about that second bit. On the right-hand side, it's the death count. So the number of decrements for each age band, in this case, deaths. And you can see that the raw data reflects what you typically expect to see as a curve of deaths with a right skew distribution. In this instance, the maximum or the mode is around something like 65, 68 years. That's driven by the fact that our exposures are skewed towards middle-aged people. So if you take the death count on the right-hand side and divide it by the time exposed to risk, what you get is hazard rate or death rate, usually denominated mx. And I've plotted this on the left-hand side on a logarithmic scale. That's very useful because of the exponential growth of mortality by age. So it's much easier to capture any structures and visualize the structures if you take the logarithm on the y-axis. And again, we have age on the x-axis. The black dots or circles represent the raw data. And just because we can, we just put a straight line through it. This straight line, which everybody's familiar with how to parameterize the straight line, we've got an intercept and a slope. That's actually the mortality law of Gompertz, Benjamin Gompertz. And you can see that for the central ages, say 40 to 70 or 80, that straight line is a very good fit. It doesn't really capture the excess mortality for younger ages, which we would consider like something like the accident hump, especially for males. And it's not really doing a great job at the oldest ages, at least apparently if we look at just the crude rates on their own. However, because this is not always reflective of what's going on, that looking at the crude rates, we're just looking at ratios that don't have any weight. But if you want to properly weight how much exposure or experience is actually encapsulated in each of those observations, you have to look at the residuals, which is the chart on the right-hand side. So you'll see that the residual chart here, which is essentially in units of standard deviation against age, you can see that for the youngest ages, our model really isn't doing a great job. We have residuals that exceed 2, which means that they're outside the 95% confidence band, which would be between minus 1.96 and plus 1.96, 2 for short. But the other thing is that this experience, this excess mortality experience that we appear to have between age 90 and 100, that's not actually that credible, because you can see the dots that are associated with that here in the residual chart are well within that 90% confidence band. So this is simply random fluctuation. It may just be noise, so we don't need to worry about properly fitting it. And that's the thing. We're trying to fit a model. We want to make sure that the model actually reflects the structure that we see in the experience and not random noise. So let's try out another couple of models, because since we have the data at hand, that's what you like to do. We've got an alternative mortality law, which we call the Perks law, which is literally just a logistic function. And if I do the back and forth, you can see that there's very little difference between the two on a large scale. And if you look closely at the ages 90 to 100, so the last square up in the top right-hand corner, you can see that the Perks line moves down a little bit. So there's a deceleration of mortality embedded in the Perks mortality law. Bad news is it doesn't actually fit the data any better than Gompertz. So these two laws, Gompertz and Perks, are actually the foundation for linear models, which we'll see in a minute. And we just remember they don't actually do that great a job, although for the central ages, they actually fit reasonably well. So let's move on. We've got we do need to actually try and figure out how to model that younger age mortality better. And lo and behold, we just by choosing a different mortality law, the one that everybody's probably heard about from Macom, just by adding a single additional parameter, we actually can come to grips with the entire curve really nicely. So first of all, you see on the left-hand side in the crude rates, you see that our model nicely follows the hockey stick shape of slightly excess mortality for the younger ages, and then a straight line for the ages above 50. And if you look at the residual chart, you can tell that we're really doing a good job, because virtually all of the data is within -2 and +2, with a couple of outliers, which is what you expect if you actually have real data. Now, I can't let you go without showing you my favorite model, which we call the Macom-Beard model, which was proposed by R.E. Beard, I think, in 1954. And that kind of combines the idea of Perks with the idea of Macom with a little twist. Again, we have the same problem that it doesn't really make a big difference. If I flip between the two models, it's really difficult to spot the difference. And you can also quantitatively confirm that those two models are really equivalent. So it's up to the actuary to choose which one they want to use. So let me introduce you to those models now that I've shown you the cartoon. These are the 4 models that we've just looked at. Okay, so on the top line, we've got the Gompertz mortality law. It goes back to Benjamin Gompertz in the 19th century. And the way I like to parameterize it is mu, the force of mortality, equals e to the alpha plus beta x, where if you take the logarithm on both sides, you literally get a straight line, which is what we were looking at on the first chart. So we've got an intercept alpha and a slope beta. So beta describes how we are aging, and alpha describes our inherent mortality at birth, right? The intercept. If you generalize this just a little bit and make it a logistic function, that's what Perks did. And again, you can apply a transform, the logit transform, and you get back to a straight line. So that's why these two models are actually linear models, whereas Macom and Macom-Beard break that linearity. So Macom added his Macom factor, which you normally know as a capital A or a capital C, but which has to be positive. And we apply a little trick so that we can easily fit the parameter. Our epsilon here, e to the epsilon, is the Macom factor. And the epsilon, the parameter, actually can range from -infinity to +infinity, so we don't have to constrain our fit. So that's pretty neat. We've got a Macom factor, and that's the thing that helped us get the hockey stick shape. Now, again, I'm a big fan of the Macom-Beard model, and there's a particular reason for that. So the Macom-Beard model is you take the Perks, you add the Macom factor in the numerator, and in the denominator, you add a Beard parameter, the rho, which actually is really useful when you're interested in extreme age mortality. And that's the reason why I'm fascinated by it. If you look at extreme ages, if you take x to infinity, let's say 120, then your force of mortality will tend towards a constant, e to the minus rho. And rho can be positive or negative. If it's positive, you actually have a mortality plateau. And if it's negative, you still have mortality deceleration, but the plateau is higher than 1, which is what you would get with the Perks model. Okay, now let me stop boring you with the geeky stuff, and let's just pick a model and keep going. So which model would you like to choose? Well, in this instance, we're going to go with the Maker model because it's nice and simple. It's got a nice intuitive explanation, and it's simple enough that we might even have a chance of remembering it later on. So let's go. What do we want to do? We don't want to just look at mortality in aggregate. We actually want to understand how mortality differs by different risk factors. I mentioned 4 different risk factors at the beginning. We want to look at gender, smoking status, cost of insurance type, and product. So let's start with gender. That's the obvious suspect, the usual suspect. And if you just plot the model without including gender on the left-hand side, you see that the male mortality, which is represented by the yellow dots, systematically exceeds our model, and the female mortality, the crude rates that are represented by the black dots, actually are overestimated by our model. In other words, the residuals for females are mostly negative, and the residuals for males are mostly positive. So our model isn't any good. Let's improve it. And with a very simple trick, I can actually split males and female in my model. And lo and behold, I get 2 different hockey sticks. One for the males that sits above, and one for the females that's below, representing lower mortality for females. And I always like to look at these charts because it confirms whether my model did its job, whether I actually hit the data. Very often you get a fit and you think you get statistically significant parameters and you're entirely missing the data. You're just fitting randomness. So in this instance, we actually did a great job. We've created a model that includes gender, and we can confirm that if we look at the gender-specific residuals, they actually nicely behave. They're between -2 and 2, except for this one outlier out here, which is completely harmless. And for the males, we've got a lower outlier at age 73 or so. Those are just random outliers. So it's a great model. Let's proceed. Now, you might have heard that smoking's even worse than being a man. So if you're a smoker, you've got excess mortality, which you can see very clearly in a model that doesn't include smoker. It underestimates your mortality if you're a smoker, and it overestimates your mortality for non-smokers. The reason why the line is closer to the non-smokers is simply because there's more of them, and they've got greater weight in the fit. But the residuals look really bad. So we need to improve our model to allow for smoking. And this is the proof that it's possible to do so. The non-smokers above, we have the black dots shown in the residual chart in the top right-hand corner that corresponds to the difference between the black line and the black dots on the left-hand chart. And you can see that apart from a couple of outliers that are less than 5%, which is great, we have a good model between -2 and 2, and for the smokers as well. So the question that you hopefully have now is, how did he do it? Right? Or how did you actually allow for the different risk factors in your model? And I'll give you a very quick explanation of how that actually worked. Now, remember, we took the Makeham law, which I've just put here as a reference, so we can see the difference. And first, we add main effects for gender. So with using males as the baseline, we would include an additional parameter for females. And we're only looking at main effects, so we shift the intercept. So we adjust the alpha, the intercept parameter, if you're a female. So the ZF is an indicator variable. If it's 1 for females and 0 for males. So for males, this component here disappears. And we do the same thing for smoker. We've got an intercept. We shift the mortality upwards if you're a smoker, and we don't change the baseline if you're a non-smoker. That nearly does it, but not quite. We actually have to allow for the age shape of the mortality differences between males and females, smokers and non-smokers. And the way we do that is by including interaction terms that look like this. Now, for gender, you saw that the hockey stick for males was higher, much higher and more curved than for females. And we can actually get that to work by adding a negative epsilon for females. So we've included an interaction between the Macomb term and gender, female, in the exponent of the Macomb factor. And here, for the slope, we've actually changed the slope for smokers. So by adding these 1, 2, 3, 4 additional parameters that we fit in the model, we've actually improved our model substantially, and we can prove that quantitatively using information criteria. So, are we done? As far as the age shape of mortality is concerned, yes. But if you know anything about life insurance, you know that mortality changes over the life of a policy. So by policy duration, mortality will change. So on the left-hand side, just plotting our results is the black line, and the accrued experience are the black dots. And we can see that in the early policy years, we're totally overestimating mortality. Guess what? That's called the selection effect. So, and the residual chart on the right-hand side proves that we somehow need to take care of selection, otherwise our model is not going to be any good. I just want to show you this whole thing split by cost of insurance type, because this is building up to my punchline coming soon. If you look at the selection pattern on the right-hand side for the risk premium above, the black dots for the ART business, you can see that that slope, that deterioration trend in the mortality is actually steeper for the ART business than for the level business, which is represented by the yellow or golden dots. You can see on the left-hand side that the level cost of insurance business seems to be sold to older people, so it starts off higher, but the ART experience catches up. So it's got a steeper slope by policy duration, not by age, interestingly enough. So if we add selection, and we do so in a very simple way, we adjust the mortality in the first 5 policy years, and then we have a slope parameter that governs the change, the deterioration in mortality over the course of a policy. Then we actually get reasonably good residuals. If you're looking closely, you can see that I'm lying to you. There's one residual that we didn't really take care of that well, but the client whose data, or a random selection of whose data I'm showing, doesn't want us to disclose a full model. So we're missing the boat on the first policy duration. But nevertheless, this is already a much better model than the one before. I hope you agree. And what we're able to do is we're able to parameterize that difference in slope here. So we're done now. We've seen anti-selection, we've seen selection, but there's one more thing that I wanted to tell you. Once we've actually controlled for all these different risk factors within our mortality model, for an individual portfolio, remember, this is 200,000 or so lives, that has been studied over a 10-year period, so it's not a huge portfolio, we can actually see a trend. So if we plot it's the same chart again, we've just changed the x-axis, it's now calendar year. And if we just plot the crude rates, which is the black dots, and our model, which is represented by the black line, we can see that in the early years, our model underestimates mortality, and in the later years, it overestimates mortality. The residual chart is even clearer. You can see that there's a pattern going from top left to bottom right, which is an improvement trend. And just by adding a single parameter into our model, we can actually get that improvement trend to work. If we include time, all of a sudden the residuals are nicely bunched around 0. Okay, so now I've shown you the process of building a model. I'll quickly show you the end result. Don't be scared by the big fat table that's coming. I'll walk you through it carefully. So remember, alpha was our intercept. So the first parameter on the top, that's our alpha parameter, the intercept. You can see that its p-value is really, really small, which means that it's a statistically significant estimate based on the entire portfolio. We've got 3,000 deaths. If we make the adjustment for females to the intercept, that's based on a little bit more than 1,000 deaths because there's roughly 1,100 females. And we even have a statistically significant estimate for smokers here, which is based on 700 deaths. But this is highly significant, even though we're only using 700 deaths, because we're borrowing the entire the statistical credibility of the entire portfolio, because we're doing a multivariate analysis. This is actually fully credible and can be used in pricing and valuation. And by the way, the client whose data I've been showing you, whose data I've borrowed, recently implemented this methodology for their valuation assumption setting. Okay, moving through the table, we've got the beta, the age component, again, based on the entire portfolio, but we've made an adjustment if you're a smoker, again, based on 700 deaths. This isn't quite as credible, but still the p-value is less than 5%. So the slope of the mortality curve for slopers is actually flatter. It's got a negative adjustment to beta. So your mortality is higher, but the slope is lower, which means that ultimately you can't tell the difference between between smokers and non-smokers. And if you remember, if we went back to the slide that showed the residuals without incorporating smokers, you would have seen that at really old ages, you can't tell the difference. Okay. The new thing, all of this is stuff that's been used in the in actuarial practice over the 15 or 20 years. But the new thing that we've contributed is actually being able to model selection using a phase, like the first phase, the first 5 years, has lower mortality, but it has a steeper slope. And modeling the anti-selective drift in mortality for the ART business. So you can see that the slope by duration is positive, it's increased. So there's an anti-selective lapse deterioration going on within the portfolio for the entire life of the business. And finally, we can see a mortality trend that this is the p-value is less than 1%, which means it's highly significant. And this parameter estimate of minus 0.027 corresponds to an average improvement rate of roughly 2.6% every year for this particular portfolio. So, summarizing the case study, we chose the Macomb law because it's nice and simple. Macomb Beard would have been just as good, but it's a little bit more complicated. So keep it simple is the most important actuarial judgment criterion. We've been able to identify differences by gender, smoker, I glossed over product, and we have a deterioration component for cost of insurance type. And then we are still able to model a selection effect, which also includes anti-selective lapse mortality deterioration. And once we've done all of that, we get a mortality improvement rate for the entire portfolio of roughly 2.6% per year. Okay, so I've still got a couple of minutes time, and I'll keep talking until Joey kills me, but I do want to show you a little bit on Singapore mortality to compare mortality in Singapore to another couple of countries. So if we look at the life tables that are published by SingStat. You can grab them off the Human Mortality Database or the Human Life Tables database at mortality.org. You can see that for the core ages that in the insurance industry we're really interested in understanding mortality, it's a nice straight line, especially for males. So let's try and use the Gompertz law, because we've got a nice interpretation for the intercept and slope, and we can use that to compare mortality between the different countries that I mentioned at the beginning. So let's have a look. So on the far right, we've got Singapore. On the top, we've got the crude rates or the published rates and a fitted Gompertz model represented by the solid line. That's the top right-hand corner. It shows mortality for females, and the bottom right-hand is for males. And for males, as I was hoping, Gompertz actually does a really good job. So it's a great way of thinking about mortality. Your level of mortality that you change with the alpha, and the slope of mortality, which is the beta. Now, just looking at these charts, you can see that there are differences, but we can quantify those differences a little bit more clearly if we use our model. So let's do that. If we look at female mortality for those 4 different countries, we can see that the Gompertz model shows that the mortality for Singaporean and Australian women is very similar, at least at those ages where the Gompertz model fits well. But maybe we can gloss over the ages 40 to 50 and focus on 60 to 90, where the bulk of the experience also was. Canadian mortality, which I was showing you the case study of, actually exceeds those 2 lines. And the Japanese women are world record holders in longevity at the moment. So it's no surprise that their mortality curve is below those others. Looking at men, we can see that they're actually all really close together, except for the Canadians that seem to have excess mortality. This is 2020, so there may be a little bit of COVID contributing to that. If we went back in time, maybe the differences wouldn't be as big. But the great thing, if you've fitted a simple Gompertz model, which is literally in period mortality, a straight line on a logarithmic scale, you can actually do that for every period and then plot the parameters. Here we go. We've got the intercept parameter alpha on the top for males in red and females in blue. And you can see that in Singapore, the slope of improvement for the intercept is actually steeper for females than for males. So female mortality has been improving faster over the last 15 years in Singapore than male mortality. That's quite remarkable because it's different from other countries. At the same time, if we look at the slope parameter beta on the bottom chart, we can actually see that mortality, the slope of mortality has been increasing. So even though mortality has been dropping, the table is becoming steeper, which means that the ages within which people die actually are being compressed. It's a phenomenon called mortality compression in actuarial science. So you can actually see that this improvement trend is matched up with a mortality compression trend in Singapore. That's already, like, just having a super simple model gives us the chance to understand that. And we can compare it to other countries. Let's take a look. This one's Canada. You can see that the mortality difference between males and females is much greater in Canada. The mortality trend is slower. The mortality compression for females is still there, but it's less than in Singapore. And for males, the beta isn't really changing. So it's just literally the mortality table is just being shifted downwards without becoming steeper. In Australia, the trend is very similar to Canada. Big gap between males and females, and different slopes for males and females. And finally, Japan, again, looks very much like the Singaporean experience, where the Japanese females are actually those world record holders in low mortality. You can see, if you look closely, if you look at the cartoon, Singapore in 2020 had virtually no impact of COVID. There's no change. Canada definitely did for males. Australia didn't in 2020. In 2021 and 22, it actually occurred. And then finally, Japan also had COVID impact. So just summarizing, we can use our simple Gompertz model to do a pretty detailed analysis of comparison between different countries, at least for ages 60 to 99. We've got a couple of interesting findings about the levels of mortality, about the slope of mortality, and about the mortality trend in these different countries. But obviously, if we take in a more complex model, we might even be able to get more information. So I think my time's up. I'd like to thank you for listening. I'd like to thank the organizers of this conference, because it's been a really great conference. And I'd also like to thank my colleague Jibril Ismail, who largely contributed to building the models that I've shown you today.
Thank you, Kai. For the audience, if you have any question, please submit in the Q&A. And here are a few I got from the chat group I have. In the mortality modeling, the data quantities can be a significant issue. In other words, there could be lack of statistical credibility. And how this issue influence the modeling techniques and their accuracy, and what strategy can be employed to mitigate such challenges. And can you please share some examples you experienced in the past?
Absolutely. Well, that's an excellent question. Thank you very much. The statistical credibility of the results obviously stands and falls with the data quality and the quantity of data. But the less data you have, the more mathematical work you have to do to actually understand whether or not it's giving you a signal or whether you're measuring noise. And the technique that I've demonstrated today is a great way of doing that. You can actually measure the error of the estimates. You can see how much experience contributed to that particular result. And you can measure the uncertainty of the entire table that you've built. Now, in my experience, if you have more than a couple of hundred deaths in your portfolio, it is possible to build a table. If you have more than a couple of thousand deaths, it's possible to build a table that you can actually use, that you can rely on, where the error is small enough that you can actually use it for valuation and pricing purposes. That's my rule of thumb. But my one of the really interesting projects that I did in the past was based on less than 800 deaths. And we were able to build very, very detailed tables that could be used for risk management because they showed differentials, but they couldn't really be used for pricing because the error associated with the results was too large. But measuring the uncertainty is the key thing that you have to do to make sure that your model is credible.
Thank you. We have a comment from the audience from Alex, and I believe it could be Alex Lee, our SAS president. So comments is for the eventual insured life table for Singapore, hope to see the credibility confidence interval shown at the different cells. Well heard. Okay, let's move to the next question. This is probably an operational questions. So for companies or team who doesn't have the program set up for the model constructions to churn out the results as what you described in the chat, and what's your recommendation on what they should do, and what options do they have?
Well, every company has a method of analyzing its experience, and the question is just whether it's how much time they actually spend on it. And ironically, the methods that I showed you, they can all be implemented in simple R scripts and are much more efficient than your traditional A over E analysis, which you actually get as a byproduct. So from an operational point of view, using more sophisticated techniques actually often saves you time. The only difficulty that you have is you need to learn the techniques. I recently did a 1-week workshop with this Canadian client, and now their valuation team is actually using these techniques. So it's not the threshold is actually surprisingly small once you just do it, like a certain sports brand suggests.
Thank you. And I will take last question. This is my own question, probably. This is Professor Ravi, who's the speaker this morning, also your good old friend as well. When I met him earlier this year in Singapore, he's a fan of machine learning for life insurance application, including mortality table construction. But he also mentioned this little work has been done so far. What's your view about it?
Ravi and I discussed this at length quite frequently, and I agree with him that there's a lot that can be done. I wouldn't say that there hasn't that it's entirely a desert. There's been a lot of work, and there are a couple of PhD theses that are coming through right now that actually deal with machine learning for mortality. There's even a textbook on actuarial learning that's available since earlier this year. So there's a lot of there are a lot of projects have started to apply machine learning in mortality modeling, but they're not yet mainstream. So there's a lot of work to be done, and I'm really excited about the opportunities to actually apply machine learning to even enhance the model. The key thing that I would add is that if you're looking at an individual portfolio, you normally don't have huge amounts of data. So I had 226,000 lines of data, 226,000 records. That's not big data in any way. And using that in a machine learning setting is overkill. You're likely to fit randomness. So you need natural intelligence, not just artificial intelligence in this instance. But as greater data sources become available, which is actually happening especially in the UK and also in Australia, I know of a really cool research project or multiple research projects using population level data to properly model the differences in mortality by a socioeconomic group in ways very similar to how I've described, applying machine learning on top of this. This has incredible potential, and I'm really looking forward to the next couple of years where we're going to see that.
Yeah, thank you very much for your view, and again appreciate for your contribution to SS and sharing of your thoughts.